everyone, this lecture is on Chapter 19, the respiratory system. What you see in this first picture are ciliated cells that move mucus through your respiratory tract. Alright, let's begin with an overview of the respiratory system. The respiratory system is specialized to bring oxygen into the body and expel carbon dioxide. It consists of passages that filter, moisten, and warm incoming air and transport it into the body, into the lungs, and to the many microscopic air sacs where gases are exchanged. It produces vocal sounds, helps with smell, and regulates blood pH. Respiration is the process of exchanging gases between the atmosphere and the body cells. It refers to the way an organism acquires energy and the oxygen required to produce that energy. Respiration consists of the following events. We've got external respiration, which is ventilation or breathing, and it allows for gas exchange in the lungs. We've got internal respiration, which allows for gas transport in the blood and the exchange with body cells. And then we've got cellular respiration, which is the process of ATP production in mitochondria, and it uses oxygen to harness the energy and gives off carbon dioxide. So we have external respiration, internal respiration, and cellular respiration. Organs of the respiratory tract can be divided into two tracts, the upper and lower. The upper respiratory tract consists of the nose, nasal cavity, sinuses, pharynx, and larynx. The lower respiratory tract consists of the trachea, the bronchial tree, and the lungs. This image shows the parts of the respiratory system. Note that the upper respiratory system, as mentioned here, goes all the way down to the larynx. So here's the nasal passages and the pharynx, and then the larynx will be right here in the voice box. The lower respiratory passage is the trachea, bronchial tree, and the lungs. And so here we see the trachea, the bronchi, and then the lungs. Let's talk about the nose. The nose consists of nostrils, which are also called external nares, and they provide openings for air to enter and leave the nasal cavity. The openings are also protected from particles by internal hairs that sometimes stick out if they get too long, right? And I also remember that nostrils are called nares because I particularly have a bad habit of flaring my nares when I'm annoyed at somebody. Flare those nares. Then the nasal cavity is the hollow space behind the nose, and it's separated into the right and left portions by the nasal septum. The nasal septum is made up of the ethmoid bone superiorly and the vomer inferiorly. And so there's actually a suture that joins those two bones, which is why people can have a deviated septum if the suture doesn't join correctly. Alright, we also have nasal concha. These are called concha because conch is like a snail, and so they're curved like a snail shell. And as you can see, they curl in from the lateral walls of the nasal cavity. Concha separate the nasal cavity into passageways called meatuses. And meatus is an opening. Like you have a auditory meatus for your ears, and you have a urinary meatus for your urinary system. The upper portion of the nasal cavity contains olfactory receptors for the sense of smell. And remember, the smell is connected directly to the part of the brain that processes smell. It doesn't go through the thalamus first, so it's a direct passageway for smell molecules to be interpreted by the brain. The nasal cavity is also lined with a mucous membrane known as pseudostratified ciliated epithelium. You saw that in the tissues lab. The pseudostratified ciliated epithelium contains goblet cells which produce mucus, and this traps dust and pathogens. It also has cilia on top of the cells because they sweep mucus towards the pharynx where it is swallowed. Pathogens and particles are destroyed in the stomach, and this prevents infection. The nasal cavity also functions in the conduction of air. It warms, moistens, and filters incoming air. The nasal concha support the mucous membrane that lines the nasal cavity and helps increase the mucous membrane surface area. And as the air travels through the concha, that's what helps to warm and moisten and filter that incoming air. And then when it's going out of the nasal cavity, the nasal concha will hold the heat inside our body and it will cool that air as it comes out, which is why oftentimes it will condense into like snot. And it's also because the temperature of your body is much hotter than cold temperature on the outside. And so that condensation causes your vapor to occur, like out of your mouth as you talk. And then again, snot and water to form. That's why you're always sniffling outside when it's cold. Okay, so this is showing the nasal concha. Let's start there. You see the superior, middle, and inferior. You can see how they curl. So they're increasing surface area and they are helping to warm and filter incoming air and cool outgoing air. We see the nares here, and flare those nares. And then this is the pseudostratified ciliated columnar epithelium. And it's pseudostratified because it is a simple tissue, even though it looks stratified. All the cells connect to the basement membrane, making it a simple tissue. And it's columnar because the cells that reach all the way up to the apical portion are going to be column shaped. And then it's ciliated with the cilia, which are microtubule extensions that go out of the cell and they can move and they help to propel the mucus formed by the goblet cells over the surface of the respiratory tract. Sinuses. Everybody knows sinuses because they tend to get flared up along with your nares. And they get flared up, though. The sinuses get flared up because of bacteria and pollen. And so they are air-filled spaces in the maxillary, frontal, ethmoid, and sphenoid bones of the skull. They open into the nasal cavity. Mucous membrane lining is continuous with the lining of the nasal cavity. So sinuses will reduce the weight of the skull. They resonate the voice, which is, again, why your voice sounds deeper to you than it does to others, because you can hear your own voice, but you hear it resonating inside your sinuses. Makes it sound deeper than it really is. That's why nobody really likes their voice when they hear it recorded, because you don't recognize it as you, but that's what everybody else hears. Sinusitis is due to the infection or an allergic reaction, as mentioned earlier, and it may result in the blockage of sinus drainage, causing sinus pressure and headache. And sometimes the sinus can be filled with a cyst, and that's terrible. So this is the sinuses here, and sometimes that can be filled with a cyst, and it can press on the trigeminal nerve and cause a lot of pain and crazy sensations, and oftentimes surgery is needed to scrape that cyst out of the sinus cavity. Ooh. Okay, here's our plug for don't smoke, right? So the effects of cigarette smoking on the respiratory system. Respiratory system damage from smoking is slow, progressive, and sometimes deadly. Smoking slows and eventually paralyzes the cilia. Dirt and pathogens can no longer be removed from the respiratory system, and this is what causes smoker's cough. So smoker's cough occurs when cilia no longer function, excess mucus is produced, and the mucus must be coughed up. Blech. Pathogens can now access the respiratory surfaces, causing more infections. Coughing leads to chronic bronchitis. Bronchial thickening results in difficulty with expiration, which is exhalation basically. Alveolar walls are destroyed, leading to emphysema. Abnormal cells may start dividing and replacing ciliated cells. Lung cancer then develops in about 20% of smokers. Environmental tobacco smoke also endangers non-smokers. My dad died of lung cancer, and he's not a smoker, but he was raised in a house full of smoke because everyone in the 50s chain smoked basically all the time. All right, the pharynx is the space posterior to the nasal cavity, oral cavity, and larynx. It is the passageway for food and air. And so remember in the digestive system chapter, we talked about how the epiglottis helps to separate the two. So let's take a look at the three portions of the pharynx. The nasopharynx is superior to the soft palate. It's an air passage, and it contains openings to auditory tubes. The oropharynx is posterior to the mouth, inferior to the nasopharynx, and it's a passageway for food and air. The laryngopharynx is inferior to the oropharynx, continuous with the larynx and esophagus. So that's a lot of pharynx, larynx, oro, mandarynx. So let's break those down again. Nasopharynx, naso is the nose and pharynx is the throat. Oropharynx, oro is the mouth and pharynx is the throat. Laryngopharynx, laryngo is the larynx and pharynx is the throat. So nasopharynx, oropharynx, laryngopharynx are the three continuous portions of the pharynx, basically your throat. Throat starts in your nose. It's kind of weird. All right. So the larynx, an enlargement in the airway superior to the trachea and anterior and slightly inferior to the laryngopharynx. The larynx moves air in and out of the trachea, and it houses the vocal cords. It's composed of a framework of muscles and cartilages bound by elastic tissue. There are three large single cartilages. The thyroid, which is the Adam's apple, is the largest cartilage, and the thyroid gland covers the lower part. The cricoid is below the thyroid cartilage, and the epiglottic cartilage is the central portion of flap-like epiglottis. So the reason it's called the Adam's apple, like the thyroid, is because it sticks out in men, and this explains also why men have a lower voice than women, because the vocal cords are larger, and so as they vibrate, they make a lower sound. And as women talk, since we have a smaller cartilage in our thyroid, we have smaller vocal cords, and our voice is higher. And hormones also play a role in that. As we go through ovulation, our voice gets a little bit higher because of estrogen. And those are kind of cues to fertility that, we, I guess, send out without really being awares of it. Isn't that interesting? Okie dokie. So also you can think about like whales and elephants, right? So they make really deep subsonic noises that can be heard for hundreds to thousands of miles. Like it's crazy. Whales can talk to each other from pole to pole. I know that sounds like I'm making it up, but I'm not. Because their vibrations are so low, they can send songs to each other from hundreds of miles away. And then elephants do the same thing. They make a really low rumbling noise that travels through the ground and can talk to each other for many, many, many miles. And this is subsonic, so we tend to have to record it and slow it down and, change it so we can hear it. Too cool. But then you think about mice, right? With their witty bitty little vocal cords, and they're just squeak, 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 squeak. Okay, anyway, enough of that. All right. So, the three pairs of smart cartilages will regulate vocal cord tension for speech and close the larynx for swallowing. And these are the small cartilage called the arytenoid, corniculate, and cuneiform. Uh-oh. Okay, sorry, my dog on alert. All right, so here we see the epiglottic cartilage, the thyroid cartilage, and the cricoid cartilages. Oh, come on now. Now my computer's going crazy. All right, so the larynx contains two pairs of horizontal folds composed of muscle and connective tissue. We have false vocal cords and true vocal cords. The false vocal cords are the upper or vestibular folds. They have no sound production and they help close the airway during swallowing. The true vocal cords are the lower folds and they produce vocal sounds, and the sound is created as air is forced between them, vibrating them. The true vocal cords plus the opening between them is called the glottis. Here we see the false vocal cord, and you can see how it's closing off the airway during swallowing. Very important. And it looks like C is showing the true vocal cord and the glottis. And you can see that opening there. Say ah. All right, the trachea, also known as the windpipe. This is a flexible cylindrical tube about 2.5 centimeters in diameter and 12.5 centimeters in length. It extends downward anterior to the esophagus. As it enters the thoracic cavity, it splits into the left and right primary bronchi. It is lined with ciliated mucous membrane, you guessed it, pseudostratified ciliated columnar epithelium, with goblet cells. The wall has 20 C-shaped rings of hyaline cartilage to prevent a collapse of the trachea. A tracheostomy is a procedure that cuts an opening in the trachea to insert a tube for air exchange. It's done, for example, if an object is lodged into the larynx or trachea. Here we see the trachea, and it's 20 awesome C-shaped cartilaginous rings. And it's C-shaped because the esophagus is behind it. And the esophagus needs to be able to expand as you swallow food and beverage. And so in the back of the cartilaginous ring will be kind of just that thin collagenous membrane and not a cartilaginous portion. So it's just at the anterior part of the trachea where that cartilaginous ring is, which is why it's C-shaped. So cool. I love it. Here's a beautiful picture of that C-shaped cartilage, and it's hyaline cartilage, which is one of the prettiest cartilages to look at under the microscope. I love all the cartilage, the fibrocartilage, the elastic cartilage, so pretty. And so again, here it is C-shaped, and then you can see the mucous membrane extends the entire inner lining of the trachea. No problem there. It doesn't mess with the function of the esophagus. And then here's the smooth muscle and connective tissue made of collagen that forms the posterior wall of the trachea, and the esophagus would sit right behind it. And there you go. This is a tracheotomy here, showing it cut open. All right, the bronchial tree. Oh, it's so pretty. It looks just like a tree. And it's amazing that the nervous system branches like a tree as well. The reason that trees branch like they do is to increase the surface area so they can maximize photosynthesis on their leaves. And so that just makes sense because the bronchial tree is going to branch the way it does to maximize the amount of air that can be inhaled and exhaled. And then, of course, the nervous system is going to branch like a tree to maximize the amount of cells and tissues that it can innervate. It's a gorgeous design. So the bronchial tree is going to consist of branched airways leading from the trachea to the microscopic air sacs in the lungs. Starting with the trachea, it branches and resembles an upside-down tree. And those successive divisions of branches from trachea to the microscopic air sacs include the right and left main bronchi, the lobar or secondary bronchi, the segmental or tertiary bronchi, the interlobule bronchioles, the terminal bronchioles, the respiratory bronchioles, the alveolar ducts, the alveolar sacs, and the alveoli. All right, so starting with the primary bronchi, those are the two largest bronchi, and they branch from the trachea and they lead to a lung. The lobar or secondary bronchi branch from the main bronchi. There's 2 on the left, 3 on the right. The tertiary bronchi each enters a segment of the lung. There's 8 on the left, 10 on the right. The interlobular bronchioles enters a lobule of the lung. There's 40 to 80 terminal bronchioles in each lobule. And the respiratory bronchioles are the first structures to conduct gas exchange. The alveoli bud from the sides of their walls. As the bronchi continue to branch, they get smaller or narrower and narrower, more narrow. And the reason they get more narrow is because it helps to slow that air down. So by the time they get to the alveolar ducts and the alveolar sacs, that air is almost like dead air. It's not really moving. And that's important because it doesn't damage the alveoli. The alveoli is just one layer of simple squamous epithelial tissue, so one layer of flat cells. And also, it increases the amount of time that the air can be in contact with the capillaries, and gas exchange can occur in the alveoli. Here is the bronchi. 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 So the left bronchus and the right bronchus, and these are the primary bronchi. And then we can see the secondary bronchus here and here. So there's two branches there. And then we see on the left there are three branches. And then we can see the tertiary bronchi. And then, of course, we would have the lobular bronchi. And then the terminal bronchioles and the respiratory bronchioles. And my apologies if I miscounted any of those. Did my best. All right. So then here we see the bronchial tree. All right, so going back here, let's take a real good look, because remember, we're looking at anatomic. So we've got right on this side and we've got left on this side. So it says that we've got two secondary bronchi on the left. And so this would be our left, so that would be the secondary there. I counted this one as a secondary, but it must not be. So 1 and 2. And then it says we have 3 secondary bronchi on the right. So it would be 1 and then 2, I guess, and then 3. Because there's 3 lobes on the right side. That's what I remember, because from what I remember, your heart sits here on the left side of the lung. And so there's 2 lobes on the left side of the lung. And so let's take a look at the bronchial tree image here. And the secondary bronchi are kind of hidden for all of the lobular bronchioles and terminal bronchioles. And you can see how beautiful that is. And it has that tree-like shape. So gorgeous. Okay, and then our beautiful alveoli. So this is the image for the simple squamous epithelium that we always use in the tissue labs. We always use this one because it really shows that single layer of flattened cells, and you can see that the alveolar sacs are going to be surrounded by capillaries where there'll be the gas exchange occurring. And so here's the alveolus, the singular alveoli, and the bronchiole. So I don't want to get ahead of myself and talk about how these alveoli stay open with like a surfactant, because I'm sure that that will be mentioned later. Okay, so structure of the respiratory tubes. The structure of the main bronchi is similar to the trachea, but they contain cartilaginous plates instead of C-shaped rings. As bronchi continue to branch, as mentioned earlier, they become narrower. It's a weird word, narrower. And the amount of cartilage decreases. Cartilage disappears in the bronchioles, allows changes in diameter for bronchodilation and bronchoconstriction. Bronchodilation is when they get wider and you can breathe in more. Bronchoconstriction is when they get narrower, and so you breathe in less. Smooth muscle becomes more prominent, and then it begins to diminish from bronchioles to alveolar ducts, where it disappears. As the respiratory tubes become thinner, the type of epithelial change. So we have pseudostratified ciliated columnar epithelium in the larger tubes. We have simple cuboidal epithelium in the respiratory bronchioles. And then finally, simple squamous epithelium in the alveoli. All right, branches of the bronchial tree are air passages, transporting air but not performing gas exchange. Alveoli provide the surface area for gas exchange. Only structures that contain alveoli can perform gas exchange, from the respiratory bronchioles to the alveoli. During gas exchange, oxygen diffuses through the alveolar and capillary walls to enter the blood. Carbon dioxide diffuses from the blood to the alveoli. So here we see an illustration really showing that one layer of flattened cells, that simple squamous epithelium, and how easy it is for that oxygen to diffuse from the alveolus into the capillary, and then from the capillary, carbon dioxide will diffuse into the alveolus. So the lungs are soft, spongy, cone-shaped organs in the thoracic cavity. They're separated from each other by the heart and the mediastinum. And the right lung has 3 lobes and the left lung has 2 lobes. The hilum is the region on the medial surface of each lung through which the bronchus and the large blood vessel enters. The hilum is a neat little structure. You see it in the kidney. That's where like the renal artery enters. You even see it in a bean. The hilum is where the kind of hinge of the little bean is going to be, and the root will extend outward from that hilum as the bean germinates, because you know a bean is a baby plant, it's a seed. So hilum is a word that's seen across biological disciplines and within different organs. So it's always going to be like that central region on which something is going to like connect. Okay, so the pleura is a double-layered serous membrane surrounding the lungs. And remember, serous is going to have 2 layers. The visceral layer is the inner layer, which is attached to the surface of the lung. And the parietal pleura is the outer layer, and it lines the thoracic cavity. And so pleura is going to be the serous membrane is made up of a simple squamous epithelium, and you know it as like mesothelium. And you've heard of mesothelioma before. That's the cancer of that. So the pleura. The pleural cavity is a potential space between the visceral and the parietal pleura. And it's going to have serous fluid in it. And it's also going to be important because it's going to play a role in inspiration and expiration. Let's take a moment to look at the rib cage. All right, so back here where the ribs attach to the vertebra, it's actually a joint, like a synovial joint. When you breathe in, your ribs are going to move upward superiorly. And then when you exhale, breathe out, your ribs move downward inferiorly. So they're moving on the vertebrae, kind of like a bucket handle is how the books usually describe it. Also, there's a joint here between the costal cartilage and the ribs, and it's maybe like amphiarthrotic. It's not as tough as a suture, but it is going to be pretty tough. But you can still get some movement there, if I'm correct. And then the sternum, of course, will move up and down as the lungs inhale and exhale. So the ribs are quite mobile. Here's the pleura. So see that potential space on the inside. In black here is where the serous fluid is. And it's going to be important for like pressure and inspiration and exhalation or expiration. So it says the green is the pleura, and then the blue, which looks very similar to the green to me, is the pericardium. So the pericardium is also a serous membrane, and remember it has the serous fluid on the inside, and so the visceral pericardium is connected to the heart, and the parietal pericardium is connected to the body cavity. So this connection to the body cavity is super important because again, it aids in the movement of these organs as we breathe in, and the ribs are going to expand. It's going to pull on the parietal pleura, and it's going to open those lungs up and expand those lungs so you can breathe in And then as you breathe out, the ribs are going to descend downward, and the parietal pleura is going to follow suit, and it's going to help passively move that air out of your lungs. So this is the table that reviews the parts of the respiratory system. And so you have that for your study purposes. Okay, so let's look at asbestos as a lung irritant. So you see the word mesothelioma right there. So that's what I was mentioning earlier, the cancer of the pleura. And so that's the asbestos doing that. So asbestos is a naturally occurring mineral. It's formerly used in buildings because it resists burning. Airborne fibers, however, can lead to scarring of the lungs, including shortness of breath, and can lead to lung cancer and also that mesothelioma, the cancer of the pleura. Anytime you inhale small particulates like silica, talc, asbestos, anything like that, it can irritate the lung lining. Berylliosis, beryllium is an element, again, used in some industrial applications. So it's going to be a small particulate. And in some people, exposure to the dust or vapor evokes immune response that scars the lungs and impairs breathing. Extrinsic allergic alveolitis results from long-term exposure to dust of organic origin. Acute form causes fever and breathing impairment. Chronic form changes the lungs over time. Air pollution. Microfine airborne pollutants can pass through protective mechanisms and reach the alveoli. This may worsen asthma, irritate the eyes and the lungs, and it increases the risk of heart disease and lung cancer. So not just smoking can cause lung cancer, but all of this stuff as well, these lung irritants. I did pottery for a long time, and whenever we would mix glazes and stuff like that, there was a lot of silica and other kind of metallic particulates and whatnot that were in there, and we were advised to wear masks to help protect our lungs from those particles. Even when clay dries and we were like sweeping clay up, it was recommended that you don't sweep the clay because that puts the dust into the air. Instead, you take like a wet mop or a sponge and you mop the clay up. All right, breathing or ventilation is the movement of air from outside of the body into the bronchial tree and the alveoli. The actions responsible for these air movements are inspiration and expiration, also known as inhalation and exhalation. One inspiration plus the following expiration equals a respiratory cycle. All right, so pressure. We were already talking about that a little bit before when talking about the pleura. So atmospheric pressure is the force that moves air into the lungs. At sea level, it equals about 760 millimeters of mercury. When respiratory muscles are at rest, the atmospheric pressure and alveolar pressure are equal. So here's a physics law for you, Boyle's law. Pressure and volume of gases are inversely proportional. If pressure inside the alveoli, called the intraalveolar pressure, decreases, the atmospheric pressure pushes the air into the airways. This occurs during normal resting inspiration as the phrenic nerves stimulate the diaphragm to contract downward. The volume of the thoracic cavity increases, which decreases the pressure from 760 millimeters of mercury to 758 millimeters of mercury. In response to that pressure difference, air rushes into the thoracic cavity. So here we see the lungs at rest and the air movements of inspiration. So the atmospheric pressure at rest, we have equal pressure between the alveoli and the lungs. And that's crazy that it's just 2 parts of millimeter per mercury. That is enough to cause the air to rush into the thoracic cavity. And so remember, the diaphragm contracting downward and the ribs moving outward and expanding during your inhalation. That opens up the alveoli and the bronchioles, and that decreases that pressure to that 758 millimeters per mercury, and that brings air into the thoracic cavity. Ooh, I like this. I can't say inhalation and expiration without doing it. Ah, feels good. Inhale, exhale. All right, so here is normal inspiration and expiration. So you can read through that. We can see that out rest. Up here, number 1, we're equal pressure. Inhalation, diaphragm is flattening. The rib cage is expanding. The intrapleural pressure and the intraalveolar pressure are now lower than the atmospheric pressure, and air rushes in. And then during expiration, the thoracic cavity contracts in all 3 directions, and that causes the intrapulmonary pressure to rise, and that moves the air out of the lungs. Boop. All right, normal resting inspiration. The diaphragm and the external intercostal muscles enlarge the size of the thoracic cavity. Lung expansion is aided by surface tension in the pleural cavity, and surfactant reduces the surface tension in the alveoli to help lung expansion. Remember, I said I wasn't going to get ahead of myself, but yeah, surfactant is something in your alveoli like a soap, and it helps to keep the alveoli open. Otherwise, that water would cause the alveoli to collapse, because remember, your body is like full of water, and water has this property called cohesion and adhesion. Cohesion is when water molecules stick together, and adhesion is when water molecules stick to surfaces that aren't water, like the walls of your alveoli. And so, with that, if there wasn't a surfactant, like a soap in there, to break the surface tension, it would cause your alveoli to collapse in on itself. Okay, anyway. So, maximal or forced deep inspiration requires the contraction of several other muscles to enlarge the thoracic cavity even more. And so you're using your pectoralis minors, your sternocleidomastoids, and your scalenes. So here we see again, you've got your intercostal muscles, which are between your ribs, and they pull up on there. We see the pectoralis minor. Where's those scalenes? Right here, elevates the first 2 ribs. This is your sternocleidomastoid, which is connected to your sternum and your clavicle, and that helps to elevate the sternum. So all those muscles are pulling up on your rib cage as you inhale, and your diaphragm at the same time is contracting downward. All right, so this is a summary of the major events in inspiration for your review. Normal resting expiration. Elastic recoil of lung tissues and abdominal organs occurs as tissues return to their original shape at the end of inspiration. Surface tension develops on the moist surface of the alveolar lining, and that shrinks the alveoli, but remember, they're not going to collapse because they have a surfactant. These factors increase the intra-alveolar pressure about 1 millimeters of mercury above atmospheric pressure, forcing air out of the lungs, a passive process that does not involve muscle contraction. Maximal or forced deep expiration is due to the contraction of internal intercostal and abdominal muscles. It increases the abdominal pressure and forces the diaphragm into a higher position, which pushes more air out of the lungs. All right, so let's take a look back. And so normal resting inspiration, we are still going to be using energy to do that. And then, of course, when we do maximal deep inspiration, we're really contracting our muscles. So inspiration is like an active process. Normal expiration at rest is going to be a passive process. Unless you're blowing out forcefully, then it's active. So this is showing the normal and maximal expiration. And so here we see that it's a passive process. Our muscles are all going to relax. Our diaphragm relaxes. And our atmospheric pressure in our lungs gets 1 millimeter of mercury higher than, the pressure in our lungs gets 1 millimeter of mercury higher than atmospheric, and it pushes gently the air out of our lungs. But if we are forcing it, then we are contracting the abdomen, and we're really pushing our diaphragm up there and blowing our air out. Blow out that birthday candle. All right, so there's your table of the major events in expiration for your review. Okay, respiratory volumes and capacities. Respiratory volumes are the various volumes of air that can be moved into or out of the lungs. And it has different degrees of effort in breathing, and this moves different volumes of air in and out of the lung. Spirometry, sorry, is the measurement of these air volumes. And if you do the spirometer test, you blow on the spirometer and it goes and it has that little dial that spins around and it can measure your volumes. So let's look at those three respiratory volumes: tidal volume, inspiratory reserve volume, and expiratory reserve volume. These can be measured with a spirometer. Residual volume cannot. Residual volume is going to be like what's left over, that dead air I was mentioning earlier. Respiratory capacities can be calculated by combining two or more respiratory volumes. Vital capacity varies with age, gender, and body size, and the spirometry is used to judge progression of respiratory illnesses such as emphysema, pneumonia, bronchial asthma, and lung cancer. This is a table of review for your respiratory volumes and capacities for you to take a look at. My tidal volume is pretty good, especially for a old gal like myself, and I equated a lot to swimming. All right, here's a nice view of lung volume as you go through your respiration. So there's the tidal volume here in the blue waves, which is that volume of air moved in or out of lungs during a respiratory cycle. Here we can see the inspiratory reserve volume. Look at how far up that goes. And that is the maximum volume of air that can be inhaled at the end of a resting inspiration. Let's find that expiratory reserve volume down here in Lello. And so that's the maximum amount of air that can be exhaled at the end of a resting expiration. The residual volume, let's see if it has that there. There we go. And this is the air that is left over. Where are we at? That remains in the lungs even after maximal expiratory effort. And so that's important to mention as well, because particles that are in your lungs, because of that residual volume, some particles don't ever become exhaled out of your lungs. Like I walked into a dusty building the other day. They're doing some work at the offices at my work. And sorry, I inhaled and snorted while I was talking about that. Just thinking about all those particles makes me like want to sniff them out. Anyway, it's too late now. That was a couple days ago. But I caught a glimpse of the air as the sun was shining through the little window sliver. And I was like, oh my gosh, I can't believe I just walked in here without a mask on. And I quickly exited the building. I won't go in there without a mask again because it is full of construction debris. And so I know that stuff even stayed in my lungs, because even though I tried to exhale as forcibly as I could at that moment, there was still the residual volume left over. So I was like, oh boy, put that on the books for my future lung disease. All right, moving forward. Dead air. So anatomic dead space is air in the respiratory tract that remains in conduction structures. It doesn't reach the alveoli. Alveolar dead space is air in the respiratory tract that reaches non-functional alveoli, such as alveoli associated with capillaries with poor blood flow, and this occurs occasionally. And the physiological dead space is the total of anatomical and alveolar dead space. And so anatomic dead space equals physiological dead space, which is about 150 milliliters per breath. So, all those particles. Shameful. Yep, see, I'm all stuffed up now just talking about it. Isn't that amazing that mind can make your matter change like that? I'm like, ugh. All right, so alveolar ventilation. Minute ventilation is the volume of new atmospheric air moved into the respiratory passages each minute. Minute ventilation equals the tidal volume times the breathing divided by the respiratory rate. That's a big equation there. So let's talk about what it means. Since some new air in each breath remains in the physiological dead space, another figure can be calculated to represent the actual amount of inhaled air that reaches the alveoli each minute. And that's the alveolar ventilation rate, or AVR. The AVR equals tidal volume minus the physiological dead space, then multiplied by the breathing rate. And so the breathing rate, remember, is breathing divided by respiratory rate. So this is the volume of air that reaches the alveoli each minute. And this is an important value since it impacts concentrations of oxygen and carbon dioxide in the alveoli. That's why we got to breathe in and breathe out. Breathing is something we don't think about, and we tend to take shallow breaths. I personally will stop breathing, especially when I'm concentrating. Remember, I said I was a swimmer? I do this weird thing where I can actually close my nasal passageways. I think about it like a seal. When you look at a seal or a sea lion, and they can close their nares off. So I can close like my nasal passageway, doing it right now, and it prevents water from going into your nasal cavity as you swim. And now it's just like something I do without thinking about it. And I will stop breathing, and then I'll be like, it's silly, and it makes me cough. So I'm just saying that because, you know, I don't know like how much oxygen is actually getting to my blood. Maybe that's why I'm so dang tired. I don't breathe like I should, and a lot of us don't. So we need to really practice our breathing in a safe place, not a nasty construction dust filled area. Clean air. Breathe in that clean air, everybody. We got this. All right. So, non respiratory movements. These are air movements other than breathing, and some clear the air passages, such as in coughing and sneezing. Some express emotions, as in laughing and crying, and they usually result from reflexes, but sometimes they can be started voluntarily. Here's a, oh boy, we see the word yawning already. I'm going to yawn. So here's the table of non respiratory air movements. You see coughing, sneezing, laughing, crying, hiccuping. This one's interesting. The diaphragm contracts spasmodically while the glottis is closed. And that can be that's the phrenic nerve that they were talking about earlier. The phrenic nerve, there's two of them. There's a right phrenic nerve and a left phrenic nerve, and they go in and connect to the diaphragm and move the diaphragm. So hiccuping or spasms of the diaphragm. And then yawning, a deep breath is taken. There's some hypotheses, but no established function. So again, just seeing yawning makes me want to yawn. It could be a social thing. I know that dogs yawn when they're like submitting, or if they're a little bit nervous. And speech, of course, is another one. We all know about speech. Okie dokie. So respiratory disorders that decrease ventilation. We've got bronchial asthma and emphysema. So these are two things that you're going to really see in the medical field because they're so common. So bronchial asthma is an allergic reaction to foreign antigens in the airway, such as inhaled pollen. In smaller airways, the mucus and secretions from allergic response accumulate since not many cells are ciliated, and allergens and secretions will irritate the smooth muscle, leading to bronchoconstriction and wheezing. Emphysema is a progressive degenerative disease in which alveolar walls are destroyed. Clusters of alveoli merge into larger ones, decreasing surface area for gas exchange. Alveolar walls lose elasticity and the capillaries diminish. It requires a lot of muscular effort to breathe. It's a type of COPD, or chronic obstructive pulmonary disease, along with chronic bronchitis. And the thing about breathing disorders is they can lead to acidosis. So hopefully we'll talk about that in a bit. We've still got quite a few slides to go through, so I need to hurry up. But acidosis is going to be when carbon dioxide builds up in your blood because you're not breathing it out, and that can be dangerous. So stay tuned. All right, the control of breathing. Normal breathing is a rhythmic, involuntary act that continues when a person is unconscious. Respiratory muscles can also be controlled voluntarily. So respiratory areas are groups of neurons in the brainstem that control breathing. They initiate impulses that travel on the cranial and spinal nerves, causing inspiration and expiration. And they adjust rate and depth of breathing. The main respiratory areas are going to be in your brainstem, in the medulla and the pons. So the medullary respiratory center contains two groups of neurons. You have the ventral respiratory group, which sets the basic rhythm of breathing, and then you have the dorsal respiratory group, which modifies the activity of the basic respiratory group. So the pontine respiratory groups help set the rhythm of breathing by limiting the duration of each inspiration. So here we see the pontine center up here in the pons of the brainstem, and then your ventral respiratory group, which is your basic, and your dorsal respiratory group, which helps to regulate the basic. So this is why it's involuntary. They're in your brainstem. Your brainstem is like your survival stem. It is a part of the brain. It is going to be involuntary, autonomic. So here we can see that the pontine respiratory group helps to regulate the medullary respiratory group, and then reminding you that the dorsal respiratory group regulates the ventral respiratory group. And then these all work and regulates the respiratory muscles, which regulate your basic rhythm of breathing and the changes in rate and depth of breathing. Whew! Just don't forget to breathe. I gotta do. So partial pressure. In any mixture of gases, each gas contributes a portion of the total pressure. So partial pressure is the amount of pressure each gas contributes to the total pressure, the proportional to its concentration. What is the partial pressure of oxygen in atmospheric air? Air is 21% oxygen. So most of the atmosphere is nitrogen. Only 21% of the atmosphere is oxygen. And remember, atmospheric pressure is 760 millimeters of mercury. So you can calculate that 0.21, which is 21%, times 760 millimeters of mercury equals 160 millimeters of mercury, and that's the partial pressure of oxygen. And we abbreviate that PO2. Partial pressures are a method of referring to the relative amounts of gases in a mixture instead of using concentrations. So a number of factors affect the rate and depth of breathing. Partial pressure of oxygen, partial pressure of carbon dioxide, the hydrogen ion concentration of body fluids, the degree of stretch of the lung tissue, your emotional state, your level of physical activity, receptors that include mechanoreceptors and central and peripheral chemoreceptors. The main controlling factors are usually the partial carbon dioxide and hydrogen ion concentration. So this is leading to that acidosis that I was telling you about earlier that can occur particularly if COPD is in place, because you've got to balance the carbon dioxide levels in your blood so that you can balance the hydrogen ion levels and you don't become too acidic. So let's look at the central chemoreceptors. In the ventral part of the medulla oblongata, they mainly monitor the pH in the brain. A low blood oxygen does not have much effect on them. Hydrogen ions do not cross the blood-brain barrier well, and so it's going to be the carbon dioxide. The carbon dioxide crosses the blood-brain barrier and binds to water to produce carbonic acid, which is H2CO3. Carbonic acid dissociates to release hydrogen ions. These ions are detected by the central chemoreceptors. Therefore, since the hydrogen ion concentration is directly linked to that of carbon dioxide, these two substances are often thought of as equivalent concerning acidity. An increase in carbon dioxide or hydrogen ion in blood leads to increased alveolar ventilation. So you're going to breathe out. We got to get that carbon dioxide out. Maybe that's why I finally remember to breathe when I'm holding my breath, because my carbon dioxide is increasing and my medulla oblongata is like, yo, breathe out. And usually I have to breathe in though, and then I end up coughing and it's super embarrassing. All right, so there's a reflux of the peripheral chemoreceptors and inflation reflex. So the peripheral chemoreceptors mainly sense changes in the blood oxygen levels. They're in your carotid and aortic bodies. Decreasing oxygen levels cause an increase in breathing rate and tidal volume, leading to an increase in alveolar ventilation. It usually does not cause a major response until the partial oxygen decreases to about 50% of normal value. Wow. And so the inflation reflex helps to regulate the depth of breathing. As lung tissues stretch during inspiration, the stretch receptors are stimulated. Sensory impulses travel over the vagus nerve to respiratory areas. Duration of inspiratory bursts is then shortened, and it prevents the overinflation of the lungs during forced breathing. That's a good thing. Oh boy, here we see the feedback. So it's a negative feedback. Anytime I see these dots, I know there's some kind of feedback going on. And so this is a negative feedback loop. So that's wonderful, because what that means is that it's bringing down your levels to normal. Negative feedback reduces the effect of the stimulus, and so it's going to bring us back down into normal carbon dioxide levels, normal oxygen levels, etc. This shows the vagus nerve. If you remember from the cranial nerves, the vagus nerve is going to be very important in visceral sensations, and movements. And the vagus nerve is responsible for parasympathetic nervous system activation. And so it's going to regulate your heart rate, it's going to regulate your breathing rate, it's going to regulate digestion, etc. So, very important in these involuntary controls of reflexive breathing centers. And then also, we looked at the phrenic nerve. So, we've got the vagus nerve here as well as the phrenic nerve. And recall that the phrenic nerve is going to not be a cranial nerve. This is a nerve from your cervical nerve plexus. It's a somatic nerve, cervical nerve plexus, and it's going to come down and innervate your diaphragm. The vagus nerve is going to be a cranial nerve because it stems from the brainstem. For your review, table 19.6 has factors that affect breathing. I love that these authors include tables like this after each section. That gives you a nice, brief, concise, like study card for what the literature just talked about and what I just blabbed on about. Sorry if I blabbed too much. My apologies. Okay, exercise and breathing. Yay. Exercise can greatly increase the amount of oxygen used each minute and the amount of carbon dioxide produced. This is my favorite parts about exercise, that it reminds me to breathe. So during exercise, increased breathing rate would be expected to result from a decrease in blood oxygen and an increase in blood carbon dioxide. However, although breathing rate does increase, blood levels of oxygen and carbon dioxide do not change significantly. Increased breathing rate during exercise results from these mechanisms instead. In the cerebral cortex, it signals respiratory centers to increase breathing rate when it signals muscles to contract. Proprioceptors stimulated by muscular movement stimulate the respiratory centers to increase breathing rate. This is called the joint reflex. So your muscle movements actually increase your breathing rate. That's so neat. Exercise increases demands on both the respiratory and cardiovascular systems. Both systems must keep up with demands. If shortness of breath occurs, it is typically due to the cardiovascular system not moving enough blood between the lungs and the body cells. But don't fret. As you get more fit, let's see if it talks about that soon. Nope, so I'll tell you about it. As you get more fit, you become better able to move blood between your lungs and your body cells. And so your breathing rate does not have to get so high, and you notice that your breathing becomes more steady as you get more fit. That's cardiovascular fitness, and it's extremely important in your cardiovascular health, especially as you get older, because everything, as we have seen with life cycle changes, everything decreases in its functions and just gets bad, right? So walk a few times a week. I'm so grateful I have dogs because they keep me out and about walking, because I don't want them to suffer as a result of my inability and desire to want to get out because all I want to do is sleep. But my dogs need exercise and I need exercise. And because I love them and I want to get them out and I want to exercise them, it gets me exercise. And I see this mother with 5 children, and oftentimes she's out there walking her 5 kids. And I just think that's so wonderful. She's doing what I'm doing. She's loving her kids. She's getting them out in some fresh air and exercising. And as a result, she is exercising as well. And her kids are really well behaved. I'm super impressed. Okay. So as far as alveolar gas exchange goes, the tubular organs of the respiratory system transport air into and out of lungs. Alveoli are the sites of vital processes of gas exchange between the air and the blood. Microscopic air sacs at the ends of the alveolar ducts are the alveoli. Alveolar pores may permit air to pass from one alveolus to another, providing alternate air pathways. And alveolar macrophages help clean alveoli. I love macrophages. They're white blood cells that go around and they clean up bacteria through phagocytosis, and they're part of the immune system, and they actually move around. They're like amoeba. They move around with pseudopods just like amoeba do, and they chase and fight and eat bacteria. So wild. All right, so here's showing the alveoli and the alveolar pores. We don't see any macrophages on there, but they're in there working for you. All right, let's talk about, here we're going to see surfactant because we're talking about respiratory membranes. So most of the wall of an alveolus consists of a layer of type 1 cells, which are going to be simple squamous epithelium, And then part of the wall of an alveolus is made up of type 2 cells that are secrete that pulmonary surfactant. So gas exchange between alveolar air and the blood occurs through the respiratory membrane, which consists of these structures: the alveolar wall, which is simple squamous epithelium, the blood capillary wall, which is also simple squamous epithelium, and then fused basement membranes of these epithelial layers join the walls of the alveoli and the capillary. And basement membranes are going to largely be made up of collagen. So here we see the respiratory membrane. Yay, there's our macrophage. Look at it with its little pseudopods moving around, eating stuff. And so then we see the simple squamous epithelium of the alveolus and the simple squamous epithelium of the capillary walls right here. And then, of course, we have the fused basement membranes between them, which are going to be collagen fibers. Collagen binds all of our bodies together, and all the tissues and organs in our body. If you removed every living cell from your body, you would still see all the outlines of your tissues and your organs because of the collagen that's left behind. Here's showing the red blood cells moving through the capillaries. Remember, only one blood cell can move through a capillary at a time. Ooh, you don't want no blood clots. We'll probably talk about that here in a little bit, like a pulmonary embolism. All right, diffusion through the respiratory membrane. Cell membranes are permeable to gases. Molecules diffuse from regions of higher concentration towards regions of lower concentration. To determine the direction of diffusion of a substance, it is important to know the concentration gradient. In the process of respiration, gases diffuse from areas of higher partial pressure to areas of lower partial pressure. The respiratory membrane is thin and gas exchange across it is rapid. Several factors affect the diffusion across the respiratory membrane. Increased diffusion occurs with greater surface area, shorter distance, greater gas solubility, and a steeper partial pressure gradient. Decreased diffusion occurs due to decreased surface area and a harm to respiratory membrane. Driving force for diffusion of oxygen and carbon dioxide across the respiratory membrane is the difference in partial pressures of the gases between the alveolus and the capillary. Here we see partial pressures. Okay, so here for oxygen, this is the alveolus, so we've just breathed in, and you can see that our oxygen levels are 104 millimeters of mercury, and in our capillaries over in the blue, remember blue means less oxygen, so the oxygen is at 40 millimeters of mercury, so we're going to get diffusion from the alveolus into the capillary. And then here we see that the carbon dioxide is 45 millimeters of mercury in the capillary, but it's only 40 millimeters of mercury in the alveolus. So we're going to diffuse out of the capillary into the alveolus. So it's actually quite simple. All right, the effects of high altitude. At high altitude, the air is still 21% oxygen, but the partial oxygen decreases because the atmospheric pressure is lower. So oxygen diffuses more slowly into the blood and hemoglobin saturation declines. People experience various degrees of altitude sickness. Body attempts to obtain more oxygen by increasing the heart and breathing rate and increased production of red blood cells and hemoglobin. High altitude pulmonary edema, HAPE, is severe form of altitude sickness. Sudden severe headache, nausea, vomiting, rapid heart and breathing rate, and cyanosis. Hypoxia vasoconstricts pulmonary blood vessels, sending blood under high pressure through the pulmonary circuit and raises the capillary pressure and filters. So I've heard rumor that like if you move to Denver, Colorado, you might lose like 10 pounds within the first, few months you live there because of this high altitude sickness, and you have to increase your respiration, and your metabolic rate has to work harder to get the oxygen flow, and then you adapt to that altitude, and you probably gain that 10 pounds back. All right, so anyway, disorders that impair gas exchange. We've got pneumonia, tuberculosis, atelectasis or lung collapse, and acute respiratory distress syndrome. I apologize if I butcher any of these words. I'm sure I do. Not only do I live down here in the South, but some of these words are just darn hard, and so I apologize. All right, so pneumonia, the infection of the lungs in which the alveoli swell due to edema. The alveoli become abnormally permeable. Fluids and white blood cells enter the alveoli, and this decreases the available surface area for gas exchange. Pneumonia is severe, and it has to be addressed or it is deadly. Tuberculosis is a bacterial lung infection in which dense connective tissue called tubercles form around the infection sites. These are going to attempt to wall off infection and stop the spreading. As it does so, lung tissue is destroyed and the respiratory membrane thickens as tubercles form, reducing the surface area for gas exchange. Don't they also call that consumption back in the day? Lung collapse. I'm not going to try to say the word again. I apologize. Blood vessels collapse along with the lung, and in case of obstruction, the alveoli beyond obstruction collapses. Usually the functional regions carry on enough gas exchange for the cells. Acute respiratory distress syndrome is a form of atelectasis. It made me say it again anyway. In which the alveoli collapse. It's not funny. You don't want your alveoli collapsing. Blood vessels and airways narrow, and oxygen delivery is severely impaired. Blood transports oxygen and carbon dioxide between the lungs and the body cells. As the gases enter the blood, they dissolve in the plasma or chemically combine with other substances. Two methods of oxygen transport in the blood. 98 to 99% diffuses into alveolar capillaries, enters red blood cells, and binds to hemoglobin. Oxygen loosely binds to iron, which is Fe in heme, unit of each of 4 polypeptide chains in the hemoglobin, forming oxyhemoglobin. 1 hemoglobin combined 4 oxygens. And so chemical bonds between the oxygen and the hemoglobin are relatively unstable, which is a good thing because we want to give that oxygen up to our cells for cellular respiration. The other 1 to 2% of oxygen dissolves in blood plasma. The factors which decrease the release of oxygen from hemoglobin: a decrease in the partial concentration of oxygen, an increase in the partial concentration of carbon dioxide, an increase in acidity, and an increase of temperature. Those are all going to cause an increase in the release of oxygen from hemoglobin. Fetal hemoglobin also has an affinity for oxygen, so it's going to really get that oxygen in there from the placenta and move it to the developing fetal tissues. All right, so released oxygen moves from blood into tissues, and about 75% of the oxygen remains bound to hemoglobin in venous blood, ensuring that respiratory system can adjust carbon dioxide levels and pH as necessary. So this is the hemoglobin saturation curve. Partial pressure differences cause oxygen to diffuse from the alveolus into the blood. Blood is oxygen rich, 100% saturated in pulmonary capillaries. Oxygen is transported through the blood and is bound to hemoglobin. Differences in partial oxygen cause oxygen to diffuse from the blood into the fluid around the cells. After dropping off oxygen to tissues, hemoglobin is still about 75% saturated in venous blood, and this is called oxygen poor blood. So we saw this earlier where we've got the 104 millimeters of mercury in the alveolus, and it was only like 40 millimeters of mercury in the capillaries, and so that is the driving force for the diffusion of oxygen back into the bloodstream from the alveoli. All right, factors affecting oxygen dissociation from oxyhemoglobin. Partial carbon dioxide levels. As the partial carbon dioxide levels increases, so does the amount of oxygen released from oxyhemoglobin, because we want to neutralize it. The pH of the blood, we want to neutralize this too. So as blood pH decreases, that's going to cause the acidity to increase, and the amount of oxygen released from oxyhemoglobin will increase. Blood temperature. As blood temperature increases, the amount of oxygen released from oxyhemoglobin increases. So warm blood will increase oxyhemoglobin, release of oxygen. Acidic blood will cause the release of oxygen, and carbon dioxide, which leads to acidic blood, causes the release of oxygen. So this is showing all of those factors that are going to cause the release of oxyhemoglobin. All right, last couple of slides. Cellular metabolism generates carbon dioxide as a byproduct. It's a waste product of cellular respiration. So carbon dioxide diffuses into the capillaries because the tissues have a higher partial carbon dioxide level than the capillaries. The carbon dioxide is transported to the lungs in one of three ways. It dissolves in plasma, 7% of it does, remaining as carbon dioxide. Or this one, carbaminohemoglobin. There's 23% of that, binds to hemoglobin in the red blood cells. And then we have the bicarbonate ion. 70% will be part of that bicarbonate ion. The majority is transported this way. Bicarbonate ions form as a result of a reaction between carbon dioxide and water. So I mentioned earlier that we have bicarbonate ions being released, I believe, from the pancreas in order to neutralize stomach acid, which I thought was so brilliant. I gabbed on about that in the digestive system lecture. And so here we see buffer systems again neutralizing acids in the form of bicarbonate ions made by your body. It's just brilliant. So here we see the reaction of carbon dioxide and water combining to form carbonic acid. And so carbonic acid dissociates. It's a weak acid. It doesn't completely dissociate. So it dissociates partially into hydrogen ions and a bicarbonate ion. And so this is a reaction that goes back and forth. It moves from the left to the right, right to the left as needed. And so the bicarbonate ion is a base which can then absorb the hydrogen ion to become carbonic acid, which can then go back into water and carbon dioxide, and then the carbon dioxide can be exhaled from the lungs. And so as carbon dioxide builds up in the blood, it combines with water to form carbonic acid, but carbonic acid is a weak acid which will dissociate into hydrogen ions and bicarbonate ion. This can cause the blood to become a little acidic, so the bicarbonate ion can then soak up more hydrogen ions, and then so forth and so on, and you breathe the carbon dioxide out. And so it goes back and forth and does it all day, every day. So upon reaching the lungs, bicarbonate ions diffuse back into the red blood cells, and the reaction runs in the reverse. And I just kind of took you through that. And carbon dioxide diffuses from the blood into alveoli, where you breathe it out. So this is the image showing you the carbon dioxide transport. So let's take a look here that we've got carbon dioxide from our cells that are going to be higher than the carbon dioxide in our bloodstream. And so that's going to cause us to diffuse out of our cells into our bloodstream. And then here's where we see the bicarbonate ions coming out here. And as it moves through the bloodstream, we're going to see the formation of, carbonic acid. And then we're going to see the equation move back and forth between bicarbonate and carbonic acid and hydrogen ions and water and carbon dioxide. All right, so again, your tables that are so great. This is the table that reviews how the gases enter the blood. Okay, last slide. I know you're relieved. Lifespan changes reflect an accumulation of environmental influences and the effects of aging in other organ systems. The following changes may occur. Ciliated epithelial cells will become fewer in number. Cilia becomes less active. Mucus thickens. Swallowing, gagging, and coughing reflexes will slow down. Macrophages lose efficiency in the lungs, and increased susceptibility to respiratory infections occurs. Breathing may require more effort as costal cartilage stiffens, and postural changes change the shape of the thoracic cavity. Connective tissues replace muscle in the bronchioles, hindering dilation. Bronchial walls thin and do not open as much. Alveolar walls thin and alveoli merge, decreasing gas exchange area. Ooh! So, continue to get out there and exercise, and if you smoke, decrease or quit the amount that you smoke. Even with vaping, we know that vaping can cause popcorn lung. I'm surprised I didn't mention that in here. Popcorn lung scars your lungs, just like a lot of the other particulates that we were talking about earlier. And so, do your best to just take care of your lungs, practice breathing. Don't forget to inhale and exhale, and love your lungs, because without them, you can't breathe, and without breathing, you can't live. All right. Have a great day.